we're gonna get started. Hey everyone, welcome to Blockchain Berkeley's weekly fundamental webinar series this fall. And we are talking about distributed systems and consensus this time. So my name is Simon. I've been part of Blockchain at Berkeley for a year now. And I used to teach this decal as well as the developer decal. So actually coding all this stuff together. Ayush, do you want to introduce yourself?
Yeah, sure. So my name is Ayush. It's my third year in blockchain at Berkeley, currently co-president of the club. Super excited to get to teach you all about distributed systems and consensus today, and cannot wait for some questions and engagement from the audience.
Well, let's get started. Cool. So today, the schedule of this thing is we'll first teach you about distributed system. It's likely for you, for many of you, this is the first time you heard of this thing. And for me, it was too, when I learned about this last fall. It's a pretty complicated concept, so we're gonna break it down. So we'll first talk about what is a distributed system. Then we'll look at some properties about distributed system. And we're gonna tell a little bit of a history story about Byzantine fault tolerance, which we'll dive into. But this course is about blockchain, and we'll tie all this discussion back to blockchain and see why this distributed system and consensus stuff is useful for blockchain. It will tie it back into some of the concept you learned in the earlier weeks about Bitcoin and the proof of work. So you saw that with Nakamoto, that's Satoshi Nakamoto, and proof of work. We'll discuss a little bit about that. But then we also show you some other ideas besides Bitcoin's method. And we'll wrap it up with federated consensus. So the goal of this lecture, this is not this course used to be under the CS department, but I think the fundamental lecture really, the goal is to show everyone, regardless their background or understanding of computer science, the big ideas behind these concepts. So what we'll do, we'll make it as straightforward as possible. We'll use a lot of analogies to describe this very technical concept, and hopefully you can take away some big ideas and concepts about what the system is about. So if you have any questions, feel free to put in the chat. I have opened the chat window so I can see it, but I usually also monitor the chat. Cool. So we'll dive right into it. What is a distributed system? And distributed systems related to Chris, should we ask question in the chat or the Q&A? I don't actually know how to open a Q&A. I think either one works. Jen says. Cool. All right, we'll dive into it. So we remember blockchain as a place that people work together. People do things on the blockchain. So to do anything together, we need to come to consensus. And this has been a problem that has troubled not only blockchain or computer science, but all of human history of how a society make a collective decision. So, but to make it more relevant, I always have trouble with grabbing lunch with friends. Like we never end up deciding what to eat. It takes forever. It's like the hardest thing in the world. And imagine grabbing lunch is this hard. Making any more serious decision is even harder. So we'll dive in. This lecture is all about how to make a decision together and in the context of a distributed system. So actually, let's talk about what is a distributed system and where it comes from. So this is a very, I guess, old topic that's not like originated from like say of blockchain, but back in the days of airplanes. Not back in the days of, but airplanes used to be purely mechanical machines, right? They have things they can have like things you push around, and but then in the 70s, people put computers and electronics on them. And when you put electronics on a computer and the computer's on the airplane, and the airplane is flying at such a high, very, very high up in the clouds, there's a lot of radiation happening. And radiation can flip a bit in the computer or the sensors or the circuits. Then what happens is computer will have false information. And when the computer has false information on the airplane that's controlling the airplane, that's a big trouble. Y'all maybe remember the Boeing 737 MAX instance of their software problems, or a lot of aircraft accidents happening because sensors have wrong readings. The airspeed is not right. So, this is a big problem if you really want to put computers on the airplane. So how do we deal with potentially faulty inputs or readings or computation. Like I can't really trust that my airspeed is this number, right? Like this could be wrong, But then if I just trust it, then maybe it goes wrong and I don't know, I just crash. So what do we deal with this? The solution is put multiple of them, um, so to have redundancy. So here on the right, there's an airplane, and you can see there's a bunch of different sensor, and for each sensor, we have multiple copies of them. So if one of them goes wrong, we still have other copies of it that can still tell us the majority of the readings that could be right. And even for computers, we can have multiple computers. So if one of the computers somehow failed, maybe it's a Windows, a blue screen, probably not on the aircraft, but we can still have other computers to do computation, and we can compare computation results across the um, across the computers and see which one does it right. Cool. And this is not only on airplanes; it still continues today. The SpaceX Dragon is operating at such an adverse environment. There's a lot of heat in the going through the atmosphere, and a lot of really big pressure on the aircraft, and um, so a lot of things can go wrong. Actually, I have three computers doing computation simultaneously. So if one of them fail, it'll reboot and compare results with other two computers. So make sure the Dragon spaceship is operating correctly. And something more relevant to our lives, like self-driving cars that's coming up. Self-driving cars have a lot of sensors. There's LiDAR, there's radar, there's camera, there's a bunch of other things. And there's a step called sensor fusion, which is basically trying to see, I have all these sensor data, and is there a car actually in front of me? If my LiDAR tells me there's a car in front of me, my camera says no. What do I do? Is there a car in front of me? Can I turn? These are all problems we have to deal with, that we are operating in an adverse environment, and we have potentially faulty input that we cannot trust. And you might wonder, how does this have to deal with blockchain or computer science? Well, data centers is a good example. I mean, we're doing this on Zoom right now. But if you have a Facebook profile and you want to change the profile picture to let's say a cat, but also my other phone is logged down and I want to change it to a dog, I'm trying to write to the same file from two locations, and Facebook doesn't know, should I change the picture to a dog or a cat? So you have multiple access or multiple inputs into a system, but then you want to ensure there's a consistent result, and you want to have permission controls. And these kind of database systems around the world needs this distributed system consideration of permission, access, and coordinating action and agreeing on what's actually my profile picture in the end. And Kentaro has a question on how many models of likely bits are flipped in an environment. I think that you're referring to my thing about airplane flying high and radiation flipping that. I don't have the exact numbers because I'm not an avionics expert, but I can search it up and tell you. But this does happen in high air altitude when you have a lot of radiation. But even just one bit goes wrong. Let's say you're at an airplane and one of the bit flip, maybe it's the most significant bit, then your altitude drops a lot. Then you don't even know it goes wrong. So even just one bit got flip, or one tiny fraction of the result is wrong from what's expected, then things can go horribly wrong. But in the end, this is a course about blockchain. So I want to tie this. The goal of this series of lecture is to try to get you to understand what's the connection between distributed system and the blockchain. And maybe you see from the previous slides, these are all machines happening in very adverse environment. And I think last lecture you guys talked about Bitcoin mining and pool attacks, and that was pretty adverse. There's a lot of people trying to be malicious. So you're operating at an environment that's pretty dangerous and pretty competitive. So you need to consider these kind of problems existing in other systems operating in adverse environments. So the goal of distributed system in blockchain is to create a trust without actually trusting someone. So what does this mean? Remember in blockchain, we talk about the goal of this is there's no central authority controlling this thing. There's not a company or a government entity or a bank controlling the operation or the actual what should be the state of the system, right? There's no one that decides everything. So you don't actually know who are other people on the network. Maybe you know a few people personally, but you don't know everyone, and you don't know what everyone else is going to do. But since we don't know everyone, but we want to work together, um, we want to achieve some goal in the end. In the case of a Bitcoin, is I want to send money to Ayush, right, correctly, and I want the system to correctly record that I actually send money to Ayush with that amount I want to send. So the goal of this consensus and distributed system is to create a trust that I don't actually need to trust whoever is on the network or operating these things, but by the design of the system and the mathematics behind it, I can trust that the system is going to do the right thing itself without actually having to trust the person behind it. So that's a big idea I want you to take away, that blockchain created this kind of, you can call it social engineering or coordination, that you don't actually need to trust the people operating these things, because the protocol design actually ensures you that you don't actually need to trust the people, but it's going to do the right thing. Cool. So let's talk about what's in the distributed system, because I just show you some big ideas and pictures of fancy machines. So I think you guys saw the Bitcoin network, and maybe I'm going to generalize it to more what is like a distributed system. So in a distributed system, you have nodes. You can think about these as processes or just everyone in the network. So these are those circles I draw on the graph on the PowerPoint, and these circles need to talk to each other. This is not through like Facebook Messenger or text message, but in this network, we need to move information around. We need to send information packets to each other. So there's some kind of channel that we can talk to each other. I'm not going to go into how you actually do that, but it has to exist in a network, because that's the entire point of a network, so people can talk to each other. And the goal of this network, everyone's connected to each other for what? We are trying to accomplish a common goal. And in the case of Bitcoin, is to send money. But then there's a bunch of challenges here. Because there's no central authority controlling what's going on here, everyone is running some kind of program here. There's no traffic coordinator. So in other words, there's no global clock. When you see the word clock, it doesn't mean like not everyone sees the right time, but more about the sequence of the events happening. So I will go into an example about that later. But the other thing is everyone in the network can fail. And we'll talk about failure a bit more of what that failure actually means. But imagine my Wi-Fi goes down, and I hope that doesn't happen during this lecture. But if it goes down, it goes down. There's no way I can connect to it. So if you hand to me some task and my Wi-Fi got disconnected, there's no way I can go back in relatively soon. So there's potential failure of individual components that we have to account for. So I put a big cross on there that this person in the network can mysteriously fail. And this is something we have to deal with, because my Wi-Fi gets disconnected all the time and everyone else's does. Hopefully not everyone. And I want to talk about the clock problem, which is the order between how things happen. So in a court, you can see about the traffic intersection, there are some cars go before other cars, but here there's no like a traffic coordinator. So everyone's kind of doing their own thing. And then if there's no order, bad things can happen, as you imagine at a traffic intersection. So here, if some process happen between other processes, the different order of processes happening can change the outcome of the events, basically. That's what I want you to take away with. So these are some of the challenges in the distributed system. And you see this is very chaotic. And basically everything's on fire, right? There's no ordering of events. Things can fail mysteriously, and you can't really contact them, and you don't even know who they are actually, and everyone's doing their own thing. So this is like my background, Zoom background this is my favorite meme. I'm the dog in a fire, but I want to be that dog that's really calm, drinking my coffee, which I have next to me. That this is fine. Everything's going to be all right. Everything is going to do everything is going to execute correctly. So that's what a distributed system aim to achieve, despite being in such adverse environment. Cool. So let's dive into actually questions first, but we'll dive into how that actually work and how can we operate in the fire. I think Ayush has been answering them, but if you have any, throw them in there. If not, I will move forward. All right, cool. So I'll talk about some properties of distributed system, and there's a theory called CAP theory that really embodies the key elements of it. So we basically just talk about what is a distributed system, But by the design, the nature of the system, there are some properties we have to consider. There are two things in a multi-process program or distributed system that basically means there's a bunch of things going on all at the same time. And there's a trade-off called safety versus liveness. I like to think about this in the case of a coronavirus. Safety means this will not happen. I don't want to get coronavirus. I'm going to hide in my basement, which is where I am right now. And I'll never go out into the streets. So I'll never get COVID. Basically, there's no way for me to get COVID if I don't get out of my room. But then if let's say I really like coffee and I need to get coffee, there's a chance of me, I must get coffee because I need that to work. But then if I go to the coffee store and I might get infected by this COVID because there might be coronavirus there. So there's a trade-off here, right? Like I can stay in my room and not do anything all day. I won't get COVID at all. I can go get coffee and I might get COVID, but I need coffee. So I either want to be absolutely safe or I want to do things, meaningful things. And this is a trade-off. I can't really do both, right? To be more liveness, to get more coffee, I might sacrifice more safety. To be more safe, I'm gonna get less coffee. So I hope that analogy makes sense. Basically, that's one of the first trade-off you have to remember for a distributed system. Cool. The second thing is correctness of the consensus. So we talk about I'm in a fire and I want to do the right thing. And what is the right thing actually? So the right thing has three components to it. First, the outcome of the consensus or the decision making of everyone trying to execute programs and agree on something has to, the final decision must be coming from one of the inputs from the network. So let's say Ayush and I are deciding what to eat. We're deciding burger and pizza. We can't decide to do boba because boba is not one of the input or not of the thing we propose. So the decision in the end must come from one of the proposals from one of the members of the network. So that's the first thing. That's one of the valid output a system can have. Second, everyone must agree. And we talk about that. We'll talk about that more, how everyone agree. But in the end, the goal of the system is that everyone must agree on the final result and go with it. But then, people debate and talk about things for a long time, and they never make a decision. Like me, trying to figure out where to get lunch with my friends. We will talk forever, and we couldn't terminate our discussion. So if everyone don't agree, then we're not going to do anything in the end. So we have to set a time limit. It's like in 10 minutes, we must go get lunch, decide we get a pizza or burger. So that's called termination. And in a system like this, you can think the challenge of that, because sometimes you're waiting for a computer to give you an answer, but then that Wi-Fi could go down, the electricity could shut down. They're never going to get back to you. So what do you do? Do you wait forever? Do you wait for some other people to give you the answer? So these are some of the problems we need to think about. Thanks for answering the questions. I do have a fair bit of content, so you put in the chat and you will answer your question. So these are the three elements of a correctness, what defines correctness for a distributed system. And this is what it means to achieve its intended goal of everyone agreeing on the valid input as the output and in a reasonable time. So we can terminate this decision and move on to the next one. Cool. And next, we want to go into CAP theory. This is really, really important. And this will really help you understand a lot of the distributed system concepts. So here's like a Venn diagram. And you see in the middle, there's like, usually you have Venn diagram, there's like a thing in the middle where all three components intersect. Here's like, it doesn't really intersect. So this is like, sleep, study, and social for college student. You can't really get like all of them. And that's exactly the idea I want you to take away with, is you cannot get all of them. So what are these components actually? Let's dive into it. So what is so basically CAP means consistency, availability, and partition tolerance. So these are the three letters here. Consistency, what does that mean? Consistency means everyone has the latest result. Let's say I sent Ayush money, and everyone in the network should know that actually I sent Ayush money, and they have the updated transaction. That means everyone has the latest result. And if I don't know actually how much if Ayush got my money, I shouldn't provide the state. If I don't know the most recent, most latest news, I shouldn't talk about it. So that's called consistency. It means either I tell you the result, basically means I know the latest result for sure, or I don't tell you at all because I'm not 100% sure this is the correct answer or the most recent the latest news that I have. So that's called consistency. Then there's another circle called availability. Availability means it means read and write access, but in a more simple term is if I ping Ayush, he will respond to me. And that's not like a yes or no question. It could be like a degree of availability. If I message Ayush and he replied to me instantaneously, that's really good. If he takes like 5 hours to respond to me, that's still available. He's still available. It's just like I have to wait for a long time. So this is all a degree of availability here. And the next thing is partition tolerance. Partition tolerance means we have a network. I show you like kind of like the different dots and connect each other. Partition happens whenever some part of the graph, some part of the network cannot reach the other part. That could be a regional power shutdown. That could be some Wi-Fi's got disconnected. That could be PG&E is on fire again. Bay Area don't have electricity. Like that can happen. And this is the thing we have to deal with all the time. All the distributed system, all real life system must deal with partition tolerance. There's always going to be partition happening, and we have to be resistant to it. If we're not tolerant to partitions, then if our network, if one person drop out of the network because the Wi-Fi shut down, then we can't do anything. So we must develop tolerance for partitions happening in the network. And as you can see, these are the three elements of the CAP theory. And I want to take away that you can only have two of them, either CA, CP, or AP. And it's impossible to have the same in the middle, which is all three of them. Cool. So I call this the trilemma. And in later lectures on scalability, you will learn another trilemma. So by the end of this webinar series, you should know two trilemmas. One is the CAP theory, one is the scalability trilemma, which I think some other folks will talk about. All right, but you might ask me, why can't I have all three? I want to have all three. I want to have all sleep, social, and GPA, but I only have two. So let's dive into why. So imagine these are 4 computers, and they all have a color. And what does color mean? In this case, it means like an information. It could be who Simon's gonna think we're gonna win the big game between Stanford and Berkeley. If I think Berkeley's gonna win, I'm gonna put blue. If I think Stanford's gonna win, I'm gonna put red. Right now, I think Berkeley is gonna be blue. I think Berkeley is gonna win, so everyone's blue. But then one day I changed my mind. I was like, Stanford's gonna win this year. No way, because we just beat them last year, but we keep losing all the time. So maybe they will beat us this year. So I tell computer 1, no, actually I think Stanford's gonna win this year. And computer 1 is connected to computer 2, computer 1 is connected to computer 3, computer 3 is connected to computer 4. They can all talk to each other. This is a networking channel we talked about. They tell each other, oh, Simon thinks Stanford's gonna win. So we're gonna keep our color as red because that's the team Simon thinks is gonna win the big game next year. So this is how I give it an input to the system, and they kind of update their state or the information they store. And if Ayush come and ask me ask the systems, ask the computers, what's Simon's favorite? Who does Simon think is gonna win the big game next year? And they're gonna tell them it's Stanford because it's red. All right, but then as we talk about, something can happen, such as the power shutdown or Wi-Fi or latency, or just computer 1 never talked to computer 2. If there's a partition, which I draw a line here, if I draw a line here, this is impossible. There's no way if there's a partition that Ayush can actually get the answer that Simon supports Stanford. I'll show you why here, but this is impossible to have all three. That's a big takeaway. So let me dive into why. So why is that? Because if I want to have partition tolerance, that means computer 1 and 3 and computer 2 and 4 cannot talk to each other. So the 2 lines here, they're broken essentially. They're broken telephone lines. And I tell computer 1 and 3, my favorite team is Stanford. But computer 2 and 4 still thinks my favorite team is Berkeley. Then if they need to be available, so I usually ask them what's Simon's favorite team. They're gonna say Berkeley because they have to available means they have to respond. So they must respond Berkeley. But then actually my new favorite team is Stanford. So that's not gonna be consistent. In the other case, if there's a still broken telephone lines in the middle, I tell 1 and 3 my favorite team is Stanford. 2 and 4 still think my favorite team is Berkeley. And they want to be consistent. They want to make sure the results they gave to Ayush is actually correct. So remember the meaning of available of consistency. Sorry, consistency means if I know the latest news, I'll tell Ayush the answer. If I don't know the latest result, or I'm not sure about the latest result, I'm not going to tell. I'm just going to ignore whatever Ayush's question is. So Ayush asked them what's Simon's favorite team. 2 and 4 are like, okay, let's check it 1 and 3, see if they have any updates. But I cannot talk to them because my telephone line is cut. So I'm not actually sure if Simon's team is still Berkeley anymore. So I'm not going to respond to Ayush. So that's not available because they want reply to Ayush. So that's a two case here that we cannot have all three. This explains why we cannot have all three elements here. And here, the reason we don't really talk about, the reason we always talk about partition tolerant is because it always happens in the real world, as I mentioned, because network can go down, electricity shutdown can happen, systems can fail, machines can go blue screen. So we always have to have this. So our trading off is between available and consistency. All right, so that's a cap theory, and this is not a formal proof. I just want to show you graphically why you cannot have all three. And there's always a trade-off between C and A. And it's also not an absolute trade-off, as I talked about. It's not a 1 and 0, black and white. It's more about a certain degree of how consistent you want to be, or how available I want to be. I talk about availability have a kind of like a spectrum. Like I usually can reply to me 10 seconds later or 5 hours later. That's a trade-off. That's a spectrum. And so you're always kind of balancing between C and A, the consistency and availability, but you must have partition tolerance because things can go crazy in the system. So this is a really important concept. I want you to take it away. And if you're interested more in this, you can look into more some of the CS courses at Berkeley that talk about this. But this is just like a brief introduction about what this is and what's the idea about it. Cool. Questions, or let's see how we're doing on time. I think I should probably get moving. Ayush, do you mind answering Kentara's question?
Sure.
Actually, Kentara, your question could be more relevant for the parts we're going to talk about later on when we talk about more consensus stuff. So I'm going to move to that and Ayush is going to talk about that part. So your answer might be your question might be answered that time. All right. So let's take a break from this cap theory, security, liveness, safety trade-off. Let's go back in time in the Byzantine Empire or the Eastern Roman Empire. I'm going to tell you a little story. So this is a paper. This is the Byzantine general problem was a paper about distributed system published by Leslie Lansford and some other folks. It's a very famous problem, but I'm going to tell you in a way that's more engaging than this problem. So back then, there's an army of Byzantine generals, and they're trying to conquer a city. And a city has, and it's very hard to conquer a city just by one general. So they have like 4 generals, and they're all like, or multiple of them, going into different direction attacking the city. And they can only succeed if they all attack together. But back then, it was really hard to communicate. Like right now, I can text people, or probably military, they use like GPS calls or some kind of communication that's really quick. But back then, there's no way to really send information quickly because they have to use pigeons, or they have someone going around and sending information, carrying letters. And that could be a problem because there could be a delay, right? It takes some time for the messenger to ride their horses and get to the next general. They could be killed in a way, right? Because enemies could be outside the city and trying to catch these messengers, or they can get lost because they didn't know the direction. And another problem is these generals can they can dip out. They can be like, hey, I don't want to fight the city anymore. I'm going to betray our empire. I'm going to side with the city. I'm gonna plan a plot to sabotage the effort. And so this is a very complicated problem back then. And this is the problem illustrated in the diagram. So we call the two possible faults the messenger story I just talked about, called fail stop. It means messages sent to each other maybe they cannot deliver in a timely manner, or they could, the messenger get killed, or the message get altered, or it can get lost. And or it can mean one of the general just like got sick and can't do anything. So that's fail stop. That's called the fail stop fault. And this is a fault that this is an error that all modern systems have to deal with, not only blockchain, but like Zoom has to deal with this, Google has to deal with this, Facebook has to deal with this. All kind of systems must deal with this because transmission can always fail. If my Wi-Fi gets disconnected, what's going to happen, right? So this is one type of fault. The second type of fault, it's more complicated. It's a case that the commander will like change sides or like decide to like sabotage our effort. You don't actually know what he's going to do because he might change side, and they're not being honest with you because they want to sabotage the effort. They could be malicious. They could be manipulating other people. They could be corrupted. They are not saying the correct information. So in this diagram, we can see the malicious actor. It's shaded right now. And let's say I'm Lieutenant 1. I'm a good lieutenant. And here's the city in the middle. And so the commander is on the north side. Ayush, the lieutenant number 2, is on the east side. I'm on the west side. And we're going to send messengers around. So in both cases, in here, I have two conflicting messages. The commander tells me to attack. Lieutenant 2 tells me to retreat. So I don't actually know what to do because I have one attack, one retreat. I don't know what to take. Should I throw a dice or something? And in this case, actually, Lieutenant 2 is malicious. I don't actually know that. I just know he sent the information retreat. But you can argue, okay, so commander is more superior than the lieutenant because he's the commander. So let's talk about the case of commander actually being malicious. And Lieutenant Ayush, he's actually being honest. But I still get the same message about attack and retreat. So just by the same message I get, in both cases, it's the same. Either commander or the Lieutenant 2 can be malicious, and there's no way for me to know. So I can't really make a decision here. So you see, here's a dilemma here that I don't know what to do basically, because I get conflicting messages and either one of them could be malicious. There's no way for me to figure out who's malicious. And that's called a one-third bottleneck of the Byzantine fault tolerance. So here we have 3 people, and if one of them is malicious, we're screwed. We can't do anything. We don't know. We can't make a decision basically because I don't have enough information and I cannot locate who's the traitor. But if I have more than, and so if I have less than 1/3, let's say if there's 4 people and one person is being malicious, we can actually make a meaningful decision together. Even one person is malicious and we don't know who. So to generalize this from 3 people, there's no solution for more than 1/3 or more than or equal to 1/3 of the traders. There is a solution between less than, there is a solution for if the traders accounts as 1/3 of the population. So this is an important result I want to take away, because a lot of the blockchain consensus algorithm use this limitation or this Byzantine fault tolerance setup to design their algorithm. And I'm usually going to talk about that more later in the consensus section. But just take this away. The proof is very complicated, but here's just the result and the story behind it. And you might argue, okay, so this is like a history lesson I'm giving. How does this connect to the blockchain? So let's actually put them side by side. The generals, the lieutenant, the commanders, there are nodes, there are processes. There are different, the generals are different nodes in the network trying to participate and do stuff basically. The trader generals, they are faulty or malicious nodes that I usually learned last lecture. Or if you didn't come last time, it's like they're not being honest and they're not doing the right thing. They try to sabotage other people, so they're traders. There's a geographic distance I mentioned at the start of the lecture. Everyone's from everywhere across North America. And here is distributed network because everyone's apart. there's no way to communicate really quickly because you can have unreliable messengers that get killed or get lost. I can have my Wi-Fi shut down, my computer fell miserably, my message got dropped, even the packets got lost. There's a very unreliable network and across a vast, very great distance, and it's distributed. So this is kind of the same setup here. And in the end, we have this setup because we want to do something in the end. We want to attack or retreat. And here, this is on consensus, reaching a consensus, reaching an agreement between the network. So in the Bitcoin network, it means we want to agree on the transaction log. In other blockchain system, it could be agreeing on other things. But I want you to take away the simile between these two problems, how the Byzantine generals problem apply to the blockchain problems. And I want to go back here real quick. So in the next few segments, I usually going to talk about different ways to address these challenges created by distributed system. And the first few he's going to talk about fail stop. And these are industry problems that people have been working on and implemented, and we're using these every day. Byzantine, these are malicious nodes, and these could be a lot harder because they can be malicious, and there's no way for us to know that at a glance. So it likes in a Google service, most of the server are not going to be Byzantine fault because no one data center in Google is going to be malicious to other data centers in Google. There might be transmission error, or there will be network latencies and a packet loss. That's fail stop, but there's no Byzantine. But in a blockchain, because we don't know everyone in the network, some people could be malicious, as we learned last time. So we have to account for this as well. So you see that for a blockchain network, and for the design of a distributed system consensus algorithm, it's very challenging because I have to count not only one but two problems here. But Ayush is going to tell you all how to fix that. So I'm going to hand it to him because he has a fair bit to cover.
Awesome, thank you. We'll just do a quick switcheroo here. I'm going to share my screen instead. Cool. Great, so can you all see my screen?
I can see it.
Let me open the chat. Okay. Cool, so Simon's probably going to take the questions from now on. And cool. And yeah, Chris mentioned that the chat is getting a little bit large because this is a pretty technical lecture. So I would focus on keeping up with the slides in the lecture rather than looking at the Q&A, just so you can kind of keep your head straight. So let's dive into it. What is voting-based consensus? But I was kind of tired. The distributed system stuff was a lot for me. And I just want to take you real quick to a nice island that I think is a really good destination, whether you're trying to go drink some wine on the beach, go for a yacht, go for a sail. You just relax, look at the lights, the ocean, look at all the expensive boats. Now, what is this island? This is the Greek island of PAXOS, beautiful island. And the PAXOS is a Greek island. It was its own autonomous nation in Greece, in this island. But it was also a family of consensus algorithms. So why did this come out? Basically, in PAXOS, there was a parliament. And the problem in PAXOS is that the island is so chill that you could not count on any of the parliament members to stay in the parliament the whole time. So we had to have a way to pass legislation with the assumption that we won't have a full parliament for the entire session. And that kind of relates to what someone was talking about. Some of the parliament members could fail and not even be there. So here's how they did it. There was a proposer who advocates a citizen's request and moves the protocol forward, an acceptor who basically votes on these proposals, and a learner who takes notes and carries out the result for the citizens. And to get a parliament thing passed, they would take a quorum. So they would take any majority of acceptors, and that creates a quorum. And I'll explain more about how quorums can overlap, but they basically looked at the majority and took that as the rule of thumb. But why is this important for the modern day? If you look here, this kind of describes the way that we keep records with timestamps. So the citizens would talk to a proposer and they'd be like, I want this to happen. I want soda to be only 2 ounces instead of 3 because all of my family is getting fat. And the PAX in Parliament a proposer would take this, propose it to the Parliament, acceptors, learners, and proposers would all discuss. And if the decree passes, they would write it out as the ID with a unique ID. So 1375 here is lambda omega delta alpha is the new cheese inspector. And that is a decree passed with a unique timestamp. And the learner takes that decree and broadcasts it to all citizens. So this idea is useful in broadcasting data across very large systems. So if you look at companies like Google who support very large global systems like YouTube, they use PAXOS. And it is really important to understand how they take a consensus algorithm based on voting and apply that to autonomous databases that just kind of exist and tick away in data centers. It's really cool because the data centers actually participate in their own type of voting to understand which packets of data they should accept. And that's the way that Google is allowed to, or Google is able to have you upload a file in the United States and within even 1 minute get that file, or even seconds, get that file available across the entire world. Is because this algorithm is very fast and it gives you the reliability to have data spread across multiple data centers. And the reason it's fast is because you can make security assumptions here. Google owns all of its data centers in its content delivery network. So they don't have to worry about any of the nodes acting in a adversarial manner. They only have to worry about external security so that the nodes don't get hacked. But that's a very different problem than assuming, like we do in blockchain, that some of the nodes are going to act adversarially and selfishly. So this relates, and this kind of goes back to the example I drew with Google. The legislators here are like servers, the citizens are like the clients that get the YouTube videos, and the current law that exists is like the current state of the database. And if this analogy breaks down for you in your head, don't worry about it. But it's really cool to understand how these massive systems are built today using such a novel idea. And this is a kind of a side thing. This consensus algorithm RAFT was specifically developed to refute PAXOS and make it simpler. This RAFT, this image of a raft that you see here, is actually there because it depicts a escape from the island of PAXOS on a raft. So it's designed to be understandable and easier to implement. So if you've heard of JP Morgan's Quorum blockchain, that is based off of RAFT consensus. Quick overview on how it works. They have leaders that are elected, and the leader maintains its position as a leader until it fails, meaning until it times out, until it sends corrupt data, or any way it could fail. And while the leader is leading, it sends a pulse to the other nodes to tell them that it's on, and they start accepting requests from the clients, and they spread those requests out to all of its followers. So there's basically just a series of leaders that do this all across the network, evenly spread out. So any questions on there on how these database systems work, and I guess specifically why that we can assume certain things with these systems? I think that's the most important part of that section. We don't have to deal with adversarial nodes here. That's how we can get that speed. Chris asked, why do centralized databases require consensus? That's a good question. So this is not necessarily a consensus algorithm in the same way that we talk about it in blockchains. This is a system for everybody in the database to agree that they should take a new packet of data. So if I have a YouTube video that I upload in California, it's important that it eventually reaches the rest of the network. But this system allows some security so that you can actually vote on whether or not you should take that video and add it to your estate. And that kind of is the foundational idea behind blockchain. So it's more of, it's a way to maintain partition tolerance as well. So in the case, Simon talked about this, in the case that like half the world's Wi-Fi goes down, if you have security measures like this, you can afford that to happen because the data will be agreed upon and kind of regulated to when it spreads across the network. So let's kind of dive into the blockchain part of it. You all learned about Nakamoto consensus earlier about proof of work. And the way that works, as a quick recap, is that miners solve a computational hash puzzle and they spend their computational power to grind out this hash puzzle. And the purpose of this is to prevent Sybil attacks. So the idea here is that we can add security to the blockchain because you're required to consume computational power to participate in this voting process. That's the difference between this and a PAXOS type algorithm, because over here, you're consuming a resource to get that into, to participate in the voting process. And that is kind of the key difference here between blockchain-based consensus algorithms and database style voting algorithms. So what happens is that a new leader is elected through some lottery. There's some notion of membership. We already know this because we went over this last lecture, but a leader creates a block and others vote whether or not they want to include it in their chain by doing that cryptographic validation and solving the puzzle themselves. And we're going to go into a couple different consensus algorithms today. And the question that I think we should think about is what resource is being consumed. So we know that computational power can be consumed and used in proof of work as your ticket into the voting process. But let's hit the chat and let's think about what are some other resources that can be spent during consensus in addition to computational power. If we can even just name one or two, that'll be really good. Money. Money is a good one. Network bandwidth. Interesting. That could be cool. I can think of a way that could work, but money is definitely a good one. Can you consume coffee to reach consensus? Storage space. Excellent. Updating data. Privacy is a bit subjective, but I think that there are ways. I think that answer is not wrong. Great. I think that's really good. Those are some good answers. Thank you. So I have my own mini list over here. Some people said money. So yes, a viable resource to consume in consensus is currency. We'll talk about a couple of algorithms that use that. Another one is time. Actually waiting a certain amount of time is something you can consume. Someone said updating data and storage space. That is definitely a valid one. And reputation is one as well. And that kind of relates to Steve's network bandwidth answer. And I'll explain more about that as well. So we can actually spend resources to partake in the progression of the network. And that's fundamentally important because that process makes it economically infeasible to outspend all honest nodes. And that's why the concept of a 51% attack is so powerful in blockchain systems, because you really need 51% of all of the resources or in a certain round to actually like take over the network. And it's really, really hard to do that. So that's one of the best security features of blockchain. And it's not even a security feature baked into code. It really is baked into the engineering around the incentives that keep the network alive. And I think that's one of the most amazing parts of the technology. So let's jump into a couple of them. One thing we can spend is a blockchain's native currency. So some of you might have heard that Ethereum is planning to move to proof of stake. And proof of stake is really interesting because instead of spending your computational power to solve a hash puzzle, you are actually literally spending the native currency, ETH, on staking. And you lock up that ETH. It's not liquid. You can't spend it or use it. But that is the way that you could increase the probability that you are selected to be the next block. So you randomly, the protocol randomly chooses a validator based on the proportional stake invested. And there's different flavors of this because this is not really implemented yet. But one flavor on the left is that the chosen validator creates the block and the protocol just continues with no voting. Or the other side with a little bit more security is that the validator proposes a block and then there's voting that happens. But either way, we get to the end result in which the chosen validator gets the block reward and the transaction fees. So if you think about comparing this to proof of work, if you are a miner and you have a very, very large amount of hash power, you have more probability of getting the block and finishing your puzzle faster. So proof of stake is essentially trying to mirror that by allowing you to have more stake, and that being the proportional probability that you get. There is a lot of depth to go into here, arguing whether this is as secure as proof of work. Many people think it is not. Many people think it is almost as good. But there is a lot of depth here, and I think this is a very interesting rabbit hole that you can jump into if you're interested. Great. So another is your actual activity. And this is a combination of proof of work and proof of stake resources. So what happens in this consensus algorithm is that the miners create blocks, which varies depending on the implementation. And the validator gets the block header, which is just like one part of the block that you need to validate, and they will sign the valid blocks. So there's kind of a two-layer security system here. This has also been toyed around with in some chains, and this is kind of what people refer to when they talk about a hybrid of proof of work and proof of stake. Another is burn. So proof of burn is like proof of stake, but a little bit edgier in that you actually send coins to an address that burns your tokens. And the more coins that you burn on a given round, the higher likelihood of your election to get the block reward and mine the next block. So this is a bootstrapping mechanism, and it's a really hardcore way to guarantee that the incentives of the network are correct, because you really need skin in the game here. If you want the network to progress forward, you have to put your money where that intention is. So the resources consumed here are currency, but the difference is that it's not even necessarily the native currency of the platform that you're using. You could, if Dogecoin uses proof of burn, you could potentially burn Bitcoin to participate in Dogecoin's consensus. And that opens up a whole other possibility of different types of chains that don't necessarily mirror the same core Bitcoin, Ethereum chains that we see today. Awesome. So someone in the chat earlier when I had asked said space, storage space and updating data is a resource that you can give up. And that's absolutely correct. If we want to create a decentralized web future, we're going to need storage solutions that are not centralized. And there's a couple people trying to do that right now. Namely, IPFS is a popular storage protocol that is incentivized by a coin called Filecoin. And what's cool here is that the consensus for Filecoin is based off of how much storage space that you are giving to the network. And Simon just linked an excellent talk on IPFS. I definitely recommend checking that out if you're interested in this topic. But you can use the disk space to solve a challenge. The details of that are very cool as well. And that allows you to basically reward people who are giving up a lot of space for the network. And that incentivizes the network to keep going. But it also provides security because the people who are invested in the network with lots of storage space are the ones who are going to be pushing it forward. And if you are like a small player who wants to, I guess, take over the network, it's going to be a lot tougher for you. And as I mentioned as well, there's time as a resource that really is popular today. And this is called proof of elapsed time. I know a couple protocols that use this, and it is really cool. It relies on something called a trusted execution environment. So what that is if you're curious, look up Intel SGX chips. They have trusted execution environments, and it's essentially a black box in which the computer cannot see inside. So we can trust that when you ask your TEE to make a wait of a certain amount of time, you can actually trust that the environment will wait that long, and you're not going to get some hackery or trickery with timestamps. So this is hardware dependent, so it's not as like publicly open as proof of work is per se, but it still follows the same principle that you give up time and you consume literal time to move the network forward. And that gives the same amount of security. It's actually genius because you cannot, you can't like, you can't steal time and or even like purchase time or like send it to people. So there's no way that you can gain enough time to outspend everyone else. So the first one who finished waiting wins the block reward. And finally, one thing to cover is proof of authority. This is really good for test nets. And some people talked about like privacy, identity. This is kind of that. These are used on Ethereum test nets, Kovan and Rinkabai. And it basically is not ever going to be used in a public blockchain, but it just makes the consensus way less expensive and way faster because you just have some group of central authorities sign off on all transactions. So that's why we use it for test nets. But I thought it was just cool to include here. And you can see the source code on the Ethereum GitHub here. So great. I'll pause real quick for any questions. We're doing well on time, so we can take a couple questions. Cool. So yes, I can explain proof of elapsed time really quickly again. So I'll go back. So yeah, proof of elapsed time, essentially it chooses one random person to wait a certain random amount of time. The actual implementation can depend on what the protocol is trying to do. So if it's if the protocol is like an exchange, for example, then maybe your liquidity is the parameter that gets you actually selected, along with some variation of time. But so what ends up happening is that like the person who finishes waiting first is the one who has the least amount of time assigned to them. So it's not like everybody is assigned a random amount of time or the same amount of time. It's that everyone is assigned a different random amount of time. So it's possible that you could get the shortest one, and that's how you win the block reward. So if that makes sense. Cool. So I'll go back and explain RAFT really quick as well. So yes, RAFT consensus. I'll jump to this a little bit deeper. And cool. Then I'll take Steven's question and then we can move on. So yeah, going back to PAXOS and voting consensus, RAFT is really cool because it creates multiple clusters, and this is the protocol that happens within one RAFT cluster. So in an entire network of RAFT nodes, you can have multiple clusters that are all running this protocol, and that kind of allows you to have that consistency across the network. So it's quicker because you rely on a leader. So you lean into some centralization to get the effect, the benefits of speed that come with that, and I guess simplicity that come with that. So you have a leader that's randomly elected, and the leader continues to be the leader until they fail. That leader is the sole node responsible for communicating within clients in that cluster. So the leader is solely responsible for managing the log and replicating that log across other servers of the cluster. So the leader is elected through a heartbeat, and the leader sends out pulses to the other nodes saying that it's online. If the other nodes no longer receive the heartbeat, then they kind of start an election. And that depends on implementation as well, but one is that they create an internal timer. So the first node to not receive the heartbeat will essentially become the the next leader. So yeah, I hope that clears it up a little bit. You can also read more about RAFT consensus on the JP Morgan Quorum blockchain. They have a implementation of it for their blockchain. It's pretty cool. But yeah, the main idea here is that you lean into some centralization for the trade-off of having a simpler and faster consensus algorithm. And Stephen, you mentioned your work is with private permission. This is a good, JP Morgan's Quorum uses this algorithm for that reason, because they have permissioned blockchain that they use for their clients. And then finally, I'll talk about proof of authority. So proof of authority, this is not something you should use like really ever. Even if you're trying to create a permission blockchain, this kind of takes away the whole point of having a blockchain. It's just used in it's just used in test nets so that they happen really fast. If you have a private blockchain, you should still use like a proper consensus mechanism so that you uphold the security guarantees even within the private group that you've established. But this just allows on test nets very fast authorization to happen so that you don't have to actually wait for a block confirmation if you're just trying to test out a smart contract. But cool, thanks for the questions. That was really awesome. I'm glad I could clarify some stuff. Cool, so now let's go to the final federated consensus. You have made it through quite a grueling lecture, so congratulations. And let's get into this final part. So what is federated consensus? Oops. Great. So in a distributed system, a quorum is a set of nodes that are sufficient to reach an agreement. And what if you don't trust certain nodes in the quorum? How can we assume that, but then still reach consensus? And this is where federated Byzantine agreement comes in. So what we can do is introduce quorum slices. So these are a subset of a quorum that can convince one particular node of agreement. So say you're the red node here. So basically say the purple is being malicious and blue and purple don't actually agree on what the color of the crayon is, this red one here. So they have this conversation. Purple says it's red, blue says it's green, purple says, oh, okay, it's actually green. And then they reach consensus. So this is what happens. You eventually have to join these slices together. And this is what creates a quorum intersection. Sorry, is my internet stable? Can someone just let me know? I just got it.
Yeah, you cut out for a little bit. You maybe just repeat the slide.
Sure, I'll do that.
The quorum intersection.
Cool. So I'll go back one slide. Yeah, so basically, we want to reach consensus. We want to come to an understanding of the network. And we can do that using quorum, which is basically just a majority. So how do we choose majorities in a decentralized way? The problem arises in that like it's not as simple as taking a majority because you can't trust everybody. So if you count people in the vote that you shouldn't trust, then like that's bad, basically. So cool. So you want to make sure that you have redundancy so that you don't have to rely on trusting untrustworthy nodes. So we can use quorum intersections. And it basically takes multiple quorum slices that come together and forms larger quorums. And this is good so that we can come to consensus. If this doesn't happen, unfortunately, we get disjoint quorums that agree on different things. So let's walk through an example to kind of solidify this. Say person B wants to get lunch. Want to get pizza? O and M are like, nah, it's $1 burgers today. Let's get it. So they want to get burgers. And then B is like, all right, burgers are great. Let's do it. H comes along. Can I join? I don't like Brian. I don't like B. For sure. Let's form a quorum slice. So even though H doesn't trust B, he does trust O and M. So they can form a quorum slice. And A comes along. I only trust Brian and Omkar. So I don't trust M and H. For sure. Let's join a quorum slice. So now they're in a quorum slice together. So do you see what happened here? Magically, everybody in this network trusts enough people so that they are down for the hamburger. And that's really cool because they can all come to consensus without having to trust every single person in the node or in the network. And that way, we all come to quorum together through Omkar. So even though multiple people were not trusted by multiple other people, there were enough intersections where everyone could, through like some other party, trust everybody. So what are the benefits of here? There's decentralized control. No central authority controls the consensus. There's low latency because you can actually achieve consensus in a few seconds by using multiple quorums. And there's flexible trust because you can choose who you trust and you don't have to trust the entire network. And Chris, to answer your question, absolutely, this does require some level of trust. And that's why we can have the speed increase. It's just better than trusting everybody because you can choose specifically who you trust. And if everybody does that, you can come to quorum pretty fast in the whole network because you have like overlapping sets of people that trust each other until you finally get everyone to trust each other together. Kentaro, I don't think this relates to set cover, but this is like relates to set theory as like a general topic. Great. So are there any questions on how quorum works? I'm pretty sure that's it. Yeah, so we covered a lot today. We went through distributed systems and why they exist. We went through the properties of distributed systems and why there's certain trade-offs you have to make between consistency, availability, and partition tolerance. And we also covered Byzantine fault tolerance, assuming there's some adversarial people involved in the network. How do you keep the decisions correct and safe? Then we took that and we talked about voting-based consensus that large companies like Google and Facebook and all these massive companies use. Then we talked about taking that a step further and putting money where our mouth is to spend resources to participate in that voting. And that creates a blockchain consensus algorithm. And then we talked about federated consensus, which is another topic on how to actually achieve consensus with some level of trust. And that's all we have for today. Simon, you jump in and say something else?
Actually, Chris had a great question. Yeah, he says, what blockchain use what consensus mechanism mentioned today? And I just wanna we showed you a lot of things about, but the key idea is you have to sacrifice some kind of resource, right? And that could be different kind of resources. Proof of stake is very popular these days. There's a lot of new blockchain protocols. It almost seemed like an arm race that everyone's like kind of proposing new architectures and building new things. But proof of stake is kind of moving forward. That's the one that used the native currency and use staking. But there's other interesting consensus algorithm that might be good for certain use case, like the proof of storage that the IPFS and Filecoin use, because they're a storage provider system. It makes sense for them to use proof of storage because that's what they do. They have storage and you want people to store things. So it really depends on what the goal of the blockchain system is trying to achieve. There's not like a one thing fit all thing. Like some people argue, proof of work that Bitcoin uses is the best. It's the most secure thing. That might be true. Some people agree with that. So it's an interesting kind of discussion and problem that everyone's trying to figure out, and people are proposing new things all the time. So you can read more about it, online about which ones are kind of which approach is being most popular, but I bet you in like 6 months it's going to change again. So definitely keep up the news and form your own opinion on which one you think will be good for what use case, because they can be all different. And actually, I think the next lecture is on Ethereum and proof of stake. So we will talk more in depth about one of the approach, which is proof of stake. And because Ethereum is so popular, we'll talk about how that works. And if you like Ethereum, the Ethereum lecture, I also taught Ethereum dev course in the spring. So you can check that on the Blockchain at Berkeley website. And all the videos were posted there.
Awesome. So we'll hang out here and continue to answer questions, but that is the end of our lecture today. Really appreciate